So we are here today with Ulisses Barres de Almeida, researcher at the Brazilian Centro in Physics in Rio de Janeiro. And we are in the beautiful context of the international conference Extreme 19 on extreme astronomical events. The last couple of years, 2017 and 2018, have been two extraordinary years and revolutionary years, I would say, for astronomy. Because some very important works were published and they announced the rise of a new field of research, which is multi-messenger astronomy. So, first of all, what is multi-messenger astronomy?
I think we could say that multi-messenger astronomy is the culmination of a process that has been going on in astronomy since the middle of the 20th century, in a sense, which is what we used to call the multi-wavelength astronomy. So as astronomy developed, we stopped observing only with one type of instrument, the telescopes that allow us to see the universe in visible light, and started adding different instruments to the observations, like radio telescopes, X-ray telescopes, gamma-ray telescopes, in a sequence that never stopped. And in the turn of the century, we had this breakthrough now, which is the capacity to observe not more only electromagnetic messengers, photons, light, but also particles that come from space. Particles and other types of events, like, for example, the gravitational waves. So I think that the multi-messenger astronomy is the culmination of this process of being able to observe the universe in more depth and in ever greater breadth with all the kinds of possibilities for receiving information from the cosmos.
And of course, 2017 was the year of gravitational waves, but it was also the year in which multi-messenger astronomy was discovered somehow. A very important work was published. Can you tell us something about it?
Yes, and so why do we say that multi-messenger astronomy was actually born at that event of the gravitational wave detection? Because before, well, actually since 100 years ago, if we want to be fair, we can observe some particles, which are the cosmic rays that come from the universe. But we were observing these particles, and we could not tell where they were coming from. There were difficulties in identifying the sources of these objects. So yes, it was a form of looking at the cosmos, but you cannot do astronomy or astrophysics with it, because these particles had no clear origin. And the gravitational wave detection, that particular event of the fusion of the two neutron stars, was very important for multi-messenger astronomy. It's considered the foundation of multi-messenger astronomy, or the birth of multi-messenger astronomy, because it was the first time where we could see both an event of gravitational waves, so a different kind of messenger than the photons, and together with it, identify the source by detecting the electromagnetic emission of this object. So this event, that's why we consider it the birth. It was the first time we could put the two things together and say, yes, this amazing phenomenon of the production of the gravitational waves is coming from this astrophysical source. So because of that, we can understand it better than we've ever had the possibility to.
And then the following year, 2018, another very important discovery in the sky.
Yes, the following year was, let's say, the completion of this process with the detection of a source of neutrinos. So neutrinos are very light, very weakly interacting particles, fundamental particles that travel great distance through the cosmos and are very difficult to detect. And there is an experiment in the South Pole called the Ice Cube, which is dedicated to detecting these guys. And for doing this, they have put detectors under the ice in Antarctica, covering a volume which, well, for a Brazilian, this is a pretty good reference, is equivalent to the volume of the Sugarloaf Mountain in Rio, where I work. And so you can imagine that huge volume full of detectors under the ice in Antarctica. And with this, they managed to use the ice to detect these neutrinos. And again, in this event, for the first time, so these neutrinos had been observed before from the sky by the same detector. But this was the first time when we observed simultaneously an electromagnetic event that seemed to coincide with the origin of this neutrino event. So again, we could say that not only this particle was coming to us, but we could say where it was coming from. So we could start doing astrophysics with it, understanding the origin, the sources of the particles.
And it was discovered that the source of this particle was a very extreme astronomical event called Blazar, and this conference here, you and your colleagues are attending here in Padova, is called Extreme 19. So I want to ask you how this field of astronomy on extreme astronomical events can contribute to multi-messenger astronomy.
That's right. I mean, this is a kind of object that this extreme blazer is a kind of active galaxy. So it's a galaxy with a supermassive black hole in the center, which is accreting matter and then producing jets and a lot of energy in the process. And this blazer is a particular kind of these active galaxies, because the jet of matter is pointing towards us. So they have more extreme properties than the other objects. And that's why this conference is called Extreme. And the neutrino was very likely associated to a source like this. I think this conference is the recognition that now we have to start looking at these very special objects and rare objects. Less than 1% of the active galaxies in the cosmos are extreme blazars, no? Or should be extreme blazars from our predictions. So they are very rare, but we start looking at these objects with a great focus because they might be the origin of these important particles. So it's a direct consequence of these detections that we now stop to study these objects in even more detail than we were doing before.
Ulisses, I also read that you are interested in epistemological implication of interdisciplinary research. And can we say that there is a bit of interdisciplinarity in evidence integration in multi-messenger astronomy? And are there some methodological challenges there?
Yes, we can say that. And yes, there are great methodological challenges. I think, you asked the definition of multi-messenger astronomy in the beginning, and I gave you the technical definition. We could also give a sociological definition. It's like the astronomical equivalent or the scientific equivalent of the globalization, yes? Because it's the necessary integration of everybody and everything to be able to advance the knowledge of the cosmos in a further direction. And of course, this integration comes with many challenges. Challenge of putting the people and the information together, challenging of coordinating these huge collaborations. For example, I think the neutrino paper detection has, I think, something like 2,000-3,000 authors, perhaps. So it's a lot of people involved in different aspects of the work. So this is all very complicated. And of course, all this also comes in the context of another revolution that's going on, which is the data revolution. We are not only getting more data of different type, but we are getting a tsunami of data. It's too much data coming from all the different experiments. And every new experiment that is talked about, is planned, is going to produce 10 times, 100 times, 1,000 times more data than before. So there is a big question, what do we do with this data? If we don't make this data openly available for the communities and for all people around the world and for all the scientists and all the groups, can we really extract all the information that this data is producing? So there's really a technical challenge of making this information truly useful to the maximum extent to which it can be useful.
So methodology can be dependent on sociological challenges. Thank you very much, Ulisses, for your time, and good luck for your work.
Thank you very much. Thank you.